Imagine a multi-million-dollar enterprise storage array failing. The primary database goes offline, applications freeze, and your company's entire digital infrastructure goes completely dark. You have exactly 90 minutes to prove that you can diagnose the microscopic failures, the invisible threats that brought the whole thing down.
It is the absolute definition of high-stakes diagnostic muddy waters. I mean, when you are dealing with enterprise IT architecture, the machine can't just tell you where it hurts. You have to understand the logic of the hardware better than it understands itself.
Welcome to the deep dive. Today we have a very specific, highly targeted mission for you. We are going to master the foundational knowledge and, honestly, more importantly, the underlying problem-solving logic for a premier IT certification. We are cracking the code on the NS0-094 exam.
And we're not just going to memorize flashcards today. Anyone can memorize a study guide. We're going to deconstruct the engineering philosophy behind the hardware itself. If you understand why the system was built a certain way, the exam answers just naturally reveal themselves.
Exactly. So let's look at the parameters from our source material. The NS0-094 exam is a proctored test. You get 90 minutes to tackle 60 multiple-choice questions delivered in English, which might be single or multiple response. Think about that math for a second.
Yeah, that is tight.
90 minutes for 60 questions. You have roughly 90 seconds per question.
Which means hesitation will literally kill your score. You need to instantly recognize the core concept, but you also need to confidently tear apart the distractors, right? Those incorrect options designed specifically to trip you up.
That brings us to our strategy for this deep dive. To get you in the right headspace, we are going to read the full exact text of 10 practice questions from our sources. And I'll read all 4 options A, B, C, and D.
But instead of just giving you the answer key, we're going to treat this like a masterclass in storage architecture.
We'll debate the options, push back on the assumptions, and really uncover the physical reality of the data center. Okay, let's unpack this starting at the absolute macro level.
The macro level is crucial because before we look inside the box, we have to understand how these massive systems talk to each other across vast distances.
Let's pull the first question from the source. It asks, in a fabric-attached metro cluster deployment, what is the fundamental purpose of the FiberBridge devices? And here are the first 2 options. A, to perform inline hardware compression for data traversing the long-distance links, or B, to act as the primary cluster interconnect switches for local node communication.
Right, keep going.
Then we have C, to translate standard SAS disk protocols into fiber channel for long-distance transport, or D, to provide a graphical management interface for the remote site facilities team.
So to crack this one, we really have to look at the physical limitations of cables. Let's look at option C, which is the correct concept here.
Okay.
The source defines the fundamental purpose of a fiber bridge as protocol conversion, specifically taking standard SAS disk protocols and translating them into fiber channel.
Let me stop you there, because the exam throws around acronyms like SAS, Serial Attached SCSI. I know SAS is incredibly fast for reading and writing data, but, why does it need to be translated at all? Why can't we just run a long SAS cable between 2 data centers?
Because of physics. SAS relies on electrical signals sent over copper wire. It's incredibly fast, sure, but electrical signals degrade over distance due to resistance.
Oh, right.
You can only run a SAS cable a few meters, basically within the same rack, before the signal just becomes garbage. If you need to mirror your data to a backup site across the city, copper won't make it. You need fiber channel, which uses lasers to send photons over glass fiber optic cables.
So the fiber bridge is essentially a UN translator. You have the language of SAS, which works perfectly inside the local building. But to make a long-distance phone call across the world, you need the fiber bridge to intercept that electrical signal, translate the protocol, and shoot it out as light.
That is a brilliant analogy. And when you understand that physical limitation, the distractors just fall apart. Option A talks about inline hardware compression. Compression is a data efficiency feature. It's not a protocol bridging function. It's just a plausible-sounding tech term used to distract you.
And option B mentions local cluster communication, but we just established this is for long-distance transport, not local switching.
Right. And option D, providing a graphical interface for the facilities team, that's almost comical. Facilities teams manage power and cooling. They don't use protocol bridges for their dashboards.
Makes total sense. So that bridges the gap between cities. But let's shrink our focus down to a single rack. What happens if the brain of the storage array, the controller itself, suddenly dies? This brings us to a scenario tested in question 2.
Oh, this is where we get into high availability, or HA.
Exactly. The question reads, in a dual controller high availability configuration, what physical hardware mechanism allows one node to assume the identity and resources of its failed partner? The first two options are A, a shared external flash drive containing both operating system images, or B, a proprietary wireless communication protocol between the two motherboards. Then we have C, a dedicated serial cable connecting the serial ports of both nodes, or D, a high-speed internal interconnect traversing the common chassis midplane.
What's fascinating here is the sheer speed required for a failover to be truly seamless. If controller 1 dies, controller 2 has to take over so fast that the database servers accessing the storage don't even register a hiccup. The answer is D, a high-speed internal interconnect traversing the common chassis midplane.
Okay, I have to challenge this. Look at option A. A shared external flash drive. That sounds incredibly logical, right? Both controllers just read from the same external drive, so if one dies, the other already has the data. Why doesn't that work?
Well, because of latency and because of single points of failure. If you use a shared external flash drive, what happens if that specific drive fails?
Oh, now both your controllers are dead.
Exactly. Furthermore, we aren't just talking about reading static files. We are talking about mirroring active live system memory, millions of transactions per second. An external flash drive is orders of magnitude too slow for active memory mirroring.
Ah, so they need to be directly hardwired together.
Yes, they sit in the same metal box, the chassis. And the back of that chassis contains a massive, heavily engineered circuit board called the midplane. It's the spine of the machine. The internal interconnect runs right through that spine, providing massive, dedicated bandwidth.
So they're literally sharing a nervous system that instantly rolls out option B, a wireless protocol. I mean, you would never trust enterprise data to a local Wi-Fi signal between motherboards, right? The interference would be catastrophic.
And it eliminates option C, too. A serial cable is a slow, legacy connection meant for basic, text-based management access. It couldn't handle even a fraction of the bandwidth required to mirror active memory states.
Okay, so we have our local hardware failover sorted thanks to the midplane. But neither of those controllers can do anything if they don't have power. Let's talk about the raw electricity required to run these beasts. Question 3 asks, to ensure true hardware redundancy, how must the dual power supplies of a storage controller be connected within the rack environment?
This is a classic one.
Right. Options A and B are A, to completely separate power distribution units fed by independent building power sources, or B, to the exact same power distribution unit to ensure their voltage sine waves are perfectly synchronized.
Both sound very technical.
Yeah. And then C, to an uninterruptible power supply that is dedicated solely to the cooling fans, or D, to a custom step-down transformer mounted directly above the storage equipment.
This question really tests your fundamental understanding of risk mitigation. The correct answer is A. You must connect the dual power supplies to completely separate power distribution units, or PDUs, that are fed by independent building power sources.
I am going to play devil's advocate again here. Let's look at the real world. Say I have a massive enterprise-grade power strip, a top-of-the-line PDU with a built-in battery backup. Why can't I just plug both power supplies into that one amazing strip? Isn't option B fine?
It is absolutely not fine, and that is exactly the trap the exam wants you to fall into. It doesn't matter how expensive or robust that single PDU is. If it has a manufacturing defect and shorts out, or if someone accidentally unplugs it from the wall, your entire system goes down.
Ouch.
Yeah. Relying on the exact same PDU violates the core principle of eliminating single points of failure. And notice how option B throws in that phrase about synchronizing voltage sine waves.
Yeah, that sounds super technical and intimidating, like something you definitely want.
It's pure technical word salad.
Uh-huh.
The power supplies in a storage controller convert alternating current to direct current independently. They don't need synchronized sine waves from a single power strip.
Got it. And looking at the rest, option C is just silly. Having a UPS dedicated solely to the cooling fans does not keep the storage controllers running.
Not at all.
And option D, a single custom transformer right above the rack, introduces a massive, heavy single point of failure that could physically crush or short out the equipment.
Precisely.
Yeah.
Separate the power completely, from the PDU all the way back to the breaker panels in the building.
Okay, so the power is flawless. But what happens when the power is fine, but the operating system itself is corrupted and just refuses to boot? So what does this all mean for the engineer? Question 4 brings this up. It says, during a system recovery scenario where the storage operating system fails to boot, What is the primary function of the firmware prompt environment?
This is a scary place to be.
Yeah. The choices are A, to automatically rebuild degraded RAID groups, or B, to format the root aggregate with a new file system, then C, to provide a graphical interface for viewing performance metrics, or D, to configure essential environment variables and initiate a network boot.
This is a classic disaster recovery scenario. When the main operating system is dead in the water, the system drops you into a very low-level firmware environment, typically called the loader prompt. Think of it as the absolute bare minimum amount of code required to interact with the physical hardware. The correct function here is D, to configure essential environment variables and initiate a network boot.
I always visualize the firmware prompt as the emergency life raft on a sinking ship. It is stripped down, it's uncomfortable, there are no luxuries. It's meant for one thing only, giving you a lifeline so you can pull a fresh, uncorrupted OS image from the network to get the main vessel floating again.
That is exactly how it functions. And if you keep that life raft analogy in mind, you can eliminate the distractors instantly. Would you expect a life raft to have a full gourmet kitchen? No. So option A, rebuilding degraded RAID groups, is impossible.
Because it's too complicated.
Yes. RAID logic is highly complex. It requires the full intelligence of the main operating system. The firmware life raft just doesn't know how to manage RAID.
And option B, formatting the root aggregate.
Doing that from a low-level firmware prompt would be incredibly dangerous.
Right.
It doesn't have the high-level file system awareness to do that safely. You'd likely destroy your own data.
And option C just makes me laugh. A graphical interface for performance metrics. If your OS won't even boot, you certainly don't have a GUI, and the system isn't performing well enough to generate any metrics anyway.
Exactly. No GUI in the life raft.
All right, building on OS failures. What if the OS isn't dead at boot time? What if it's actively running, serving thousands of users, and suddenly it suffers a fatal kernel panic and completely locks up? How do you even reach a locked-up machine? Question 10 jumps into this.
Let's hear it.
Which scenario necessitates the use of the out-of-band management interface rather than standard network management protocols? Is it A, the primary operating system has panicked and is unresponsive, requiring a forced hardware reset? Or B, a storage administrator needs to create a new storage virtual machine for a tenant? Or C, the aggregate containing the primary database requires an emergency volume expansion? Or D, a routine firmware update needs to be applied to the fiber channel host bus adapters?
If we break this down, we need to understand the difference between in-band and out-of-band. In-band management means you're talking to the storage system through its normal network connections. It's like walking through the front door.
Okay.
But if the OS is panicked, the front door is locked, the lights are off, and no one is answering. The correct scenario is A. You use out-of-band management when the system is panicked and unresponsive.
So what physically is out-of-band management? Is it like a separate cable?
It is a separate cable plugging into a completely separate microcomputer embedded on the motherboard, usually called a baseboard management controller, or BMC. It runs on its own independent power state. It is the back door.
Wow, okay.
Yeah, even if the main CPU is completely frozen, the BMC is still awake, allowing you to force a hardware reboot or pull crash logs.
So it's basically a highly privileged watchdog sitting outside the main system, which means we can throw out B, C, and D immediately. Creating virtual machines, expanding volumes, running standard updates, those are all routine administrative tasks. You would do all of those in-band through the normal healthy OS interface.
Correct. You don't break down the back door just to deliver the Daily Mail.
Okay, let's assume the OS is healthy. The front door is open. How does this healthy OS actually know where the data physically lives on the spinning disks? Question 5 asks, what is the hardware significance of the physical shelf ID configured on a disk enclosure?
Good question.
Options A and B are A, it dictates the speed at which the internal fans will operate, or B, it determines the logical address space assigned to the physical drives within the operating system. And option C and DC, it sets the priority for which shelf receives power during a cold start. Or D, it configures the management IP address for the specific shelf module.
If we connect this to the bigger picture of storage architecture, the answer is B. The shelf ID determines the logical address space assigned to those physical drives within the OS.
I want to clarify this for the listener. A massive enterprise array isn't just one box. It's a controller head unit connected to stacks and stacks of disk enclosures called shelves. There could be dozens of them, right?
Exactly. Hundreds or thousands of individual hard drives. The operating system needs a map. On the back of every physical disk shelf, there is a tiny digital display with a button. The engineer physically pushes that button to assign a number, say, shelf 01, shelf 2.
Right.
The OS reads that hardware ID and creates a logical map. It now knows that drive 4 and shelf 1 is definitively a different piece of physical hardware than drive 4 and shelf 2.
It's literally the street address for the data. Drive 4 is the house number, shelf 1 is the street name.
Perfect. And that entirely disproves the distractors. Option A is wrong because fan speed is governed by internal thermal sensors, not a numerical ID. Option C is wrong because power priority is not managed by this display.
And option D.
It's a distractor for networking, folks. You don't assign an IP address via a single-digit LED display on a disk shelf.
Okay, so understanding that logical map is great, but eventually a human engineer has to walk into a freezing cold, incredibly loud data center and physically touch the hardware. How do they know what to pull? Let's check. Question 8.
Let's do it.
A storage administrator observes that the fault LED on a specific drive carrier is illuminated solid amber, while the shelf fault LED is also amber. What does this specific combination indicate? The options are A, the drive is currently undergoing a routine parity initialization, or B, the disk shelf has lost redundant power from its primary source.
Okay, those are tricky.
Then we have C, a hardware failure has been isolated to that specific disk drive, or D, the drive carrier is missing its physical connection to the backplane.
This is purely about visual diagnostics on the data center floor. When you're standing in an aisle surrounded by thousands of rapidly blinking green lights, you need a clear visual language for failure. The answer is C. A solid amber light on both the drive carrier and the shelf means a hardware failure has been isolated to that specific drive.
Amber always means bad news.
Always. Green is activity, amber is a fault. If a single drive dies, its personal LED turns solid amber. But if you have 20 racks of equipment, you can't scan every single drive one by one. So the shelf itself also illuminates a solid amber light.
See.
It acts as a beacon, screaming across the aisle, "Hey, the broken part is somewhere in this specific shelf."
That is incredibly clever design, and it immediately invalidates option A. Routine parity initialization is normal activity. It would flash green, never solid amber. Option B is wrong because a redundant power loss would trigger a fault LED on the power supply itself, not on a specific hard drive carrier.
And option D is actually physically impossible. If the drive carrier is missing its physical connection to the backplane, meaning it's not plugged in all the way, it has no electrical power, an unplugged drive cannot illuminate an LED.
Basic physics wins again. So we found the broken part, now we have to fix it, or maybe swap out an entire chassis without causing any downtime for the company. Question 7 asks about this.
This is a really important one.
When performing a non-disruptive chassis replacement, why must the engineer meticulously label every cable before disconnecting the impaired chassis? A, to ensure the storage array recognizes the new chassis serial number upon reboot, or B, to guarantee all components are reconnected to their exact original ports on the new midplane. Then C, to provide documentation for the local internet service provider, or D, to prevent the cables from causing a tripping hazard in the data center aisle.
The correct answer is B. Meticulously labeling cables guarantees all components are reconnected to their exact original ports.
Because if you mix them up, you cross the streams.
That's a great way to put it. Remember, in a non-disruptive replacement, the system is actively serving data out of the surviving controller. It has a complex map of multipath I/O connections.
Right.
If you pull a cluster interconnect cable from port EUA on the old chassis and accidentally plug it into port EVRO on the new chassis, the internal logical mapping just shatters. The system gets confused, traffic black holes, and you trigger a massive company-wide outage.
And nobody wants to be the engineer who takes down a hospital's database because they couldn't be bothered to use a label maker. What about option A, though? I see the term EEPROM thrown around in study guides regarding serial numbers. Just to clarify for the listener, what is that, and why does it make option A wrong?
An EEPROM is a tiny memory chip physically soldered onto the chassis that permanently stores the unit's serial number. When you boot up, the OS reads the EEPROM to verify its licensing. Cable labels have absolutely zero impact on how a silicon chip reads a hard-coded serial number.
Excellent clarification. Option C is wrong because your local ISP does not care about your internal storage cabling. And option D, well, while preventing tripping hazards is great for workplace safety, it is not the deeply technical architectural reason defined by the NS0-094 exam objectives.
Exactly. Safety first, but that's not what the exam is testing here.
Okay, the engineer mapped the cables, swapped the hardware, the system is back online. But what about the invisible environmental dangers? Here's where it gets really interesting. Question 6.
Oh, this one is spooky.
During a controller module replacement, failing to utilize a properly grounded electrostatic discharge wrist strap primarily risks which of the following? A, causing a sudden power surge in the data center electrical grid, or B, erasing the licensing information stored on the boot media,
Yeah.
and C, triggering a false thermal alarm in the baseboard management controller, or D, inducing silent latent damage to sensitive microelectronic components.
The answer is D. Electrostatic discharge, or ESD, induces silent latent damage to sensitive microelectronic components.
Yeah. I want to focus on that word latent, meaning it doesn't break right away.
That is precisely what makes ESD the most terrifying threat to a hardware engineer. You might shuffle your feet on the floor, build up a static charge, and then touch a memory module without wearing a grounding strap. You won't even feel the spark. You plug the module in, the system boots up perfectly, and you think you're fine.
But you're not.
No. That microscopic spark carried hundreds of volts. It literally blasted a microscopic crater into the silicon pathways of a transistor gate. Weeks or months later, as the server heats up and cools down, that weakened pathway finally snaps.
Wow.
Suddenly, the server experiences random kernel panics that are completely impossible to diagnose because the hardware passes all normal health checks. It's a tiny, invisible time bomb.
That is wild. The physics of static discharge on microchips is brutal, so clearly option A is absurd. A static shock from a human is high voltage, but practically zero current. It cannot cause a surge in a massive data center electrical grid.
And option B is incorrect because static electricity doesn't surgically target and erase software licenses. Option C, triggering a false thermal alarm, is totally unrelated to the physical silicon damage caused by ESD.
So static is an invisible threat. But what about heat? Heat is very visible and very deadly. Our final question, number 9.
Let's wrap it up with a hot one.
If a high-end storage controller experiences a sudden failure of multiple cooling fans, what immediate self-preservation action is taken by the hardware? A, it migrates all active network interfaces to the management ports, or B, it initiates an automatic firmware downgrade to reduce processing heat.
Right.
C, it increases the spin speed of the attached disk drives to generate internal airflow. Or D, it triggers an automatic thermal shutdown within a predetermined time limit.
This raises an important question about exactly how hardware prioritizes threats. The correct answer is D. It triggers an automatic thermal shutdown within a predetermined time limit.
Because if those massive industrial fans die, that metal box turns into a pizza oven in seconds.
Literally seconds. The processors inside these controllers generate an immense amount of thermal energy. If the fans fail, the temperature spikes exponentially. The hardware sensors monitor this, and if the temperature crosses a critical threshold nearing the actual melting point of silicon, the system stops caring about data availability. It initiates an ungraceful hard shutdown.
Self-preservation completely trumps data access.
Always. Because an offline system can be turned back on once the fans are replaced. But a motherboard with melted, fused CPU pins has to be thrown in the garbage.
That logic effortlessly eliminates the distractors. Option A, migrating network interfaces, does absolutely nothing to cool down the boiling physical processors. Option B, an automatic firmware downgrade. Downgrading firmware is a highly delicate, slow process. Doing that while the CPU is overheating is a recipe for a completely bricked system.
And option C is my absolute favorite distractor. Increasing the spin speed of hard drives to generate internal airflow. That is pure science fiction. Hard drives are sealed units. Spinning their internal platters faster does not magically turn them into cooling fans for the chassis.
It sounds like something out of a bad hacker movie.
Exactly. The machine shuts itself off to survive. That's the only real option.
Looking at all these incredible fail-safes we discussed today, the mid-plane interconnects mirroring millions of transactions, the out-of-band management doors, the dedicated power redundancies, and the automatic thermal shutdowns designed to save the silicon. If a truly catastrophic data loss occurs on modern enterprise-grade storage hardware today, is it really a failure of the machine? Or is it ultimately a failure of the humans who designed the redundancies? Stay curious, everyone. We will catch you next time.